Okay, this is part 3 of a sequence of videos describing noise in op-amp circuits. And in part 1 we introduced the models that we use to talk about noise in the op-amp itself and in the two resistors in this circuit. In part 2 we computed the noises at the output due to each of these noise sources. And so the noise at the output due to the op-amp is given by this expression. It's equal to the input referred noise, which is a parameter of the op-amp, times the non-inverting gain. The noise at the output of the op-amp due to R1 is given by this expression. And this is equal to minus V1, where V1 is the RMS noise generated by R1 times the ratio RF over R1. And finally, the output due to the noise generated by RF is just VF. It has a gain of 1. So we'll actually get rid of the messy circuit diagram here and use the extra space to compute the output RMS noise value. The output RMS noise value will be the square root of the 3 different noises that I've computed, each of those squared. Again, the reason for this is that noises, or when you're dealing with noise, powers add, and you need to take that into account when you look at total noise voltages. So it's not noise voltages that add, it's noise powers. Okay, so basically what we have here then is the 3 noise terms. And we've squared each of those, and then we'll take a square root. So VON, this guy, is the square root of, or we'll have the square root of Vn squared times 1 plus RF over R1 squared plus V1 squared times RF over R1 squared plus, oh my, that's an ugly plus sign, where'd that come from? Plus VF squared. And so we're taking the square root of all of these guys. It's kind of a mess. Again, Vn we get from the equation that, or we get Vn from the spec sheet of the op-amp. We multiply Vn by the bandwidth, or the square root of the bandwidth. I'm sorry, we multiply the value off the spec sheet by the square root of the bandwidth to get Vn. V1 and Vf we get using the square root of the formula for the thermal noise power generated by R1 and RF. So that's pretty much it. You can go through and work these for several different examples and see the relative weighting for under different circumstances for the noise generated by the op-amp and the noises generated by R1 and RF. So at that point, we'll pretty much call this finished. What I would like to do is just recap the process to make this hopefully clear in terms of what we've done. In order to determine the noise power at the output, we have shorted the input of the amplifier circuit, this part, to ground, because we don't want to know what the response of the circuit to an input signal will be. We want to know only what the noises internal to the circuit are doing to it. We first find the output noise value due to the input referred noise of the op-amp. We then found the output noise value due to the thermal noise generated by R1, and found the output noise generated by the thermal noise in RF. And then to get the actual RMS output noise voltage, we took the output noises due to each of these three different sources, summed them, added them up, squared them first, added them up, and then took the square root. And that gives us the RMS value of the output noise voltage. So, hopefully this is clear. Hopefully it makes it easier to understand what we're doing with all these noise values and how we're computing noise values in these circuits. So, with that, we will conclude. Thanks for watching.